Hi, my name's Nathaniel Tagg. I'm a professor at Otterbein University, which is in central Ohio. I know the answer to the physics question which Martin posed today on the channel, so I thought I'd share it with you much the same way I would teach it to my introductory physics students. So the problem here is we have a marble that's going to roll down a hill, right? So the very simplest way one can think about this is using energy. Although we could go through it mechanically, talking about forces and torques, that's actually not the easiest way of doing it. The easiest way of doing it is usually to think about energy. So if I think about an object that rolls down a hill, right? So let's say it's like a toy car, right? So I have a toy car and it's got little wheels and it rolls down the hill and it winds up at the bottom of the hill. Because the wheels we can assume are really good wheels, that there's no rubbing or friction, then there won't be energy lost due to heat. So if that's the case, all of the potential energy that the car had at the top of the hill gets converted into kinetic energy at the bottom of the hill. So all the energy it had because it was up high now gets lost to making the thing go voom. We know the equations for these, right? So we know that the potential energy that it had at the beginning is equal to the kinetic energy it had at the end. So at the beginning, it has a potential energy of m times g times h, where h is how high up we started. G is the acceleration due to gravity, about 9.8 meters per second, and m is the mass of the cart in kilograms. So the kinetic energy is 1/2 mv squared, where v is how fast it's going at the end. And we see one nice little thing. It doesn't matter how much weight you pile on the cart. The velocity that you get at the end is equal to root 2gh. So you can always predict how fast the thing is going if you just know how high the hill is. This is one of the reasons roller coasters work the way they do, is it doesn't matter how many people are loaded into the roller coaster, they'll still go down at the same speed. Now, if we have a rolling ball, the situation changes. So let's do a rolling ball. So there's a rolling ball up at the top and a rolling ball at the bottom. Now, interestingly, we can hold to the same approximation here. Although there is friction between the slope and the ball never rubs on the slope if it's rolling without slipping. So if the ball slides down, this goes out the window. But if the ball is rolling down, at no point do you lose any energy to the environment because there's never any rubbing between those two surfaces. So if we do it this way, that everything stays the same, except there's a new form of energy that we have to account for. And that is that at the end, the ball is spinning as well as rolling. The ball is rotating. Or another way to put it is the top of the ball is going faster than the bottom of the ball. And so we have to account for that speed difference. The middle of the ball is going at the speed of the ball. The bottom is going no speed at all, and the top is going quite quickly. But that actually adds to the total energy because of that pesky square in there. So if we want to just write down the equation that governs this, we'd write, okay, the initial potential energy is equal to kinetic energy because it's moving, plus the kinetic energy because it's rolling, the rotational kinetic energy. So this is again going to be 1/2 mv squared plus 1/2 I omega squared. Okay, well, what are these new symbols? I is the moment of inertia. So this describes basically the mass distribution of the sphere. It gets bigger if the sphere gets heavier, but if the mass is further outside to the sphere, then it's harder to make it spin. It takes more energy to make it spin. The omega is a measure of how fast it's spinning. This is radians per second, and we don't need to get bogged down to the details of that too much. But now we can work up a complete understanding of it. So in this case, mgh will again be 1/2 mv squared plus 1/2, and for a sphere, I always have to look this up. The moment of inertia is 2/5 mr squared, where r is the radius, where r is the radius of the ball. So this is 2/5 mr squared. This is not, YouTube worthy, but I'm doing it anyway. Times omega squared. So this is the I just substituted. Okay. Now, interestingly, you can see again that the m's cancel out. It doesn't matter how heavy this ball is. Any ball where the mass is uniformly distributed, so a small marble or a big marble, will reach the bottom of the hill going the same speed, which is kind of neat. Now, this omega here is related to the v. If the ball is rolling, then it's spinning faster, right? So if I imagine a ball that's rolling on a flat plane, then these two guys are related with the velocity is equal to the spinningness multiplied by the radius of the ball. So that's the radius of the ball there. Now, if the ball is, as Martin describes, over-rotating, which is not a term I would use, but maybe engineers use it, the radius that it's spinning around is now smaller. It's a smaller radius than that. And so here, we'd use this smaller radius, the radius of between where the ball's center and where the ball makes contact with the rails it's on, and that is our new radius of rotation, so I could call that omega little r. So big R is the size of the marble, and little r is the distance between the center of the marble and the contact point when looking at it in profile. So how can I use this? So I can substitute into here. So I take my original equation, GH is equal to 1/2 v squared plus 2/5, 1/2 times 2/5 is 1/5 r squared. And now I can substitute this in for this. So I get omega is v over little r, all squared. So now if I simplify that, GH is 1/2 v squared plus 1/5 big R squared over little r squared times v squared. And so now we can combine our terms. So this is 1/2 plus 1/5 big R squared over little r squared times v squared. So I can then write down my final answer that the speed squared is equal to GH over, in fact, let's make this, let's multiply by 10 here. Let's make this 10 GH over 5 plus 2 r squared over little r squared. Just pause to check my math there. So one thing you can see is if the ball is rolling on the flat plane, big R and little r are the same thing. It's rolling at the same radius as the sphere. So in that case, you would get v squared equals 10 GH over 7. And that is in fact the slowest the marble can go, is at the speed determined by this. Right? H here, it looks like in your case, H is about like 10 centimeters or so. So we could put some numbers in if we cared about, but in fact, this isn't what we mostly need to know. Now, if we reduce this radius, this little r, then this number becomes bigger. And if that number becomes bigger, then the velocity becomes smaller and the ball isn't rolling as quickly. And so we can do that. But there is a practical limit to that. And basically, that is you can move this axis all the way up into the middle. You can't make the ball stop moving, but you can bleed off some quantity of its energy into rotation. Now, before we move on, I want to say one thing that I think Martin's missed in his design, and I'm really worried about. And that is that the energy of the ball is still there. So when the ball, so here's the track, the ball starts off here basically not moving. At the bottom of the track, it's going with some speed and it's got some rotation. So the problem here is that when this thing then hits a flat plane, it drops off the rails, which are holding it at this over-rotation point. And now it hits something else, or it drops down and hits something else. So what you're doing is you're taking a ball that's moving along at some clip, but it's also spinning very quickly. In fact, more quickly than it's moving. So if you hit a friction plane here, the ball is going to take off. It's going to, it'll suddenly translate that kinetic energy back into translational energy, into kinetic energy. So the problem here is what I think is going to happen. I think I saw this happening in the video. Is when the ball falls into when the marble falls into the to the lane underneath of it, it will hop, it will jump. You've suddenly given a lot of energy, and of course this is bumpy. So when it's spinning really fast and it hits a bump, it might take off. So I'm worried that the problem with using over-rotation as the solution is that's going to happen. Now, if you want to hang on, I'll show you the exact math for what the over-rotation gets you in terms of that velocity, but I think this is the dominant effect, and you really have to think about this. A better way of slowing down the balls might be to have them create friction with the balls as they're rolling down. For instance, you could make the, if the channel were exactly the same shape as the ball, it would rub. Or there's other things you can do to make the ball, and of course you're an expert at this point, of how to make the ball slow down by friction, putting more jags into the track, stuff like that. I don't know if you have room to do that. Okay, so if you actually want to know the answer to the question you posed, which is what's the speed you're going to get depending upon that overshoot, well, let me give you the nitty-gritty math here. I'll pull out my horrible notes that I went and dashed off the minute I saw the video because I really wanted to work this out. So what you wanted to know is how fast the ball is going to work as a function of the angle you're cutting your track at. So I'm assuming that you're using this as the angle of the track, and I'll call that angle theta. And then a ball will fit into that thing like this, right? And the radius of the ball is still big R. But now what we're concerned about is if we drop down a vertical line, we care about this, that's going to be little r. So if I draw this in profile, just one side of it, here's the ball touching, here's the radius of the ball touching it, and of course this has to be at right angles. If I have a line touching a sphere, it can only touch it at one point, and that has to be at 90 degrees to the axis. Then this is below the center of the ball by little r. And so I can draw a line. This goes straight down to the bottom of the track. So now this angle in here is theta over 2, so it's half of this angle. I know this isn't 90 degrees, and I know, and I have this little bit here. So this is the bit I need to know. Now, one thing I can do here is I can drop across a horizontal line and then look at this angle in here. So I can call this angle alpha. And what I see is that alpha and theta over 2 are complementary. So that tells me something. So I know that, and so I'll come back to that. So if I look at this little triangle up here, I know alpha, because if I know theta over 2, I know this side is little r, this side is big R. Well, that's pretty simple trigonometry. This is a cosine, that's the adjacent side and the hypotenuse. So cosine alpha is little r over big R. But since alpha is the complement of theta over 2, I know that cosine alpha is equal to sine of theta over 2. All right, so now I've got it. So little r over big R is equal to sine of theta over 2. Now, in fact, this might be a little bit easier. What we wanted to know is we wanted to know big R over little r all squared. So that's going to be 1 over sine squared theta over 2, a thing that comes in a fair amount when dealing with physics. There's actually a nice half-angle formula that lets you convert this. So this is actually equal to 1 minus cosine theta over 2. So now we can take that and we can pop that back into our original formula. So we know we have v squared is equal to 10 gh over, checking my math again, 5 plus 2 big R squared over little r squared. So now using our new thing, over 5 plus 2 times 1 minus cosine theta over 2. So this is equal to 10 gh over 6 minus cosine theta. And there you have it. That is, in fact, the best you can do. In the limiting case, theta becomes 180 degrees. So that's when you open the track all the way open. So if you have almost no angle in your track, you open that way up to 180 degrees, then that's basically the same as the ball rolling along a flat plane. And so this number becomes 1, and so it's 10. It becomes 10 sevenths. Jumping my math again. So theta equals 180 degrees. Cosine theta becomes -1. So this becomes 6 minus 1, and that's 10 sevenths, which is the same result we got earlier. So that's great. If theta gets really small, now this is the interesting case. So if I make the two channels really, really narrow, right, the ball would have to ride way up high in that channel. But now the ball is touching almost at the axle, right? So if I do that, theta goes to 0, And so cosine theta goes to 1. So this becomes 10/5 GH. But oh, wait a minute. That's just like v squared equals 2GH, which is what we found for a sliding object. So you can go anywhere between an object that's a ball that's rolling, which is the slowest possibility, where your angle is very, very flat, to the same speed as an object that was sliding, where the object is going very, very fast, which is the maximum speed you can get. Again, if you go to these extremes, if you go to this extreme, all that energy is still there, and we still have to worry about it. So I hope this helps a little bit. I don't know if any of this geometry and trigonometry can be converted into anything useful for a wider audience, but I could do it, so I did. Hope this was clear. Please feel free to shoot me any questions. My email address is ntagg@otterbein.edu. Thanks for watching.